Molecular orbitals can generally be expressed as linear combinations of atomic orbitals that are centered on each of the atoms in a molecule. So we can generally write something like this for a molecular orbital. If this is my molecular orbital, it is going to be some linear combination of a whole group of atomic orbitals of various types that are centered on each of the atoms. Now, these can represent more than one orbital on a given atom, and in that case, this molecular orbital can begin to reflect some of the shape of the molecule, but this, may be an excessive number of different orbitals that one would need to include in this linear combination. So one of the things that we can do perhaps to simplify this is to begin to build in compound atomic orbitals that actually reflect the shape of the molecule. Well, let me illustrate what I mean by an example. Let's suppose that we have a three-atom molecule, triatomic molecule, where the atoms all lay along a line. All right, and let's say two of these atoms are hydrogen, so that makes it simple. They're just in 1s orbitals, so those are the 1s orbitals we're going to use to make the molecular orbitals. But now this central atom here has s orbitals and p orbitals, but only has one s orbital perhaps of an appropriate energy to interact with these two 1s orbitals that we have on either side. So instead what it might do is it might use both its say 2s orbital, and maybe I should draw that a little bigger, and its 2p orbital. Okay, but we'll use the 2p orbital that is in the direction that this is in, and we'll again specify the internuclear axis to be the z-axis. All right, so remember that this p orbital is one that the two sides of the p orbital are going to have different sign, which I'll usually use different colors to differentiate the sign of that. So somehow this central atom is going to use these different orbitals to do that. All right, but we would end up doing some sort of variational calculation or some sort of self-consistent field calculation to ultimately construct those. But another way might be to simply create a linear combination of the 2s and the 2p orbitals on this central atom and see what that gives us. So for example, I could create an orbital that looks something like this. I'll call them phi plus or minus, but it could be the 2s orbital plus or minus the 2p, and we'll say it's the 2pz orbital. Now, ordinarily, I want to normalize these things, so I might add a normalization constant, and for two normalized orbitals, that would just be 1 over the square root of 2. But this will now produce two orbitals, one of which, I'll redraw my triatomic molecule out here. One of these, when I add the plus version, is going to be a big orbital pointing in this direction with a smaller one in this direction. So again, to differentiate the sign of these two lobes, I might do that. All right, the other orbital would be the minus combination, so it would be pushing this in exactly the reverse direction. So in this case, our big orbital is pointed toward the other atom, and our small is pointed toward the one that is not involved in that bonding. So these would represent the two results of phi plus or minus. All right, well, I hope you recognize that what we've done here is essentially create something that we know of from general or organic chemistry as a hybrid orbital. So let's define a hybrid orbital is basically going to be an orbital constructed. It's an atomic orbital constructed from primitive atomic orbitals. And by primitive, I mean basic atomic orbital, like S, P, D, and so forth. So another way of thinking of this is it's like a compound atomic orbital. Now, do you have to do this to get the right answer? The answer is no. What we're doing is we're creating this atomic orbital with a specific geometric shape. So in this case, my specific geometric shape is to indicate that these three atoms are all on a line. This is a linear molecule. And I want orbitals that stick out in the two directions opposite to one another, basically with 180 degrees between them. And so by constructing these hybrid orbitals, I'm able to construct an atomic orbital that has the right geometry. Moreover, what I'm going to insist is that these orbitals all be orthonormal to one another. So I effectively want my hybrid orbitals to represent an orthonormal set. Okay, remember that orthonormal means that each of the orbitals is normalized, so that's why I added this factor. And they're orthogonal, which means that when I find the integral of two of these, so for example, if I was to integrate phi plus star phi minus d tau, I would get 0. They would be orthogonal to one another. It doesn't necessarily look like that initially, but that's what would result. So let's look at another example of doing one of these hybrid orbital things, and I'll use BF3 as the molecule that for some reason I want to actually model in this case. All right, now I may or may not know, but I'll tell you that BF3 is a planar molecule in which the three bonds are separated by 120 degrees. All right, so all of these are at 120 degrees. And I've drawn it here in artificially in the XZ plane, which means that the y-axis is perpendicular to this XZ plane. Okay, so how might I organize these orbitals? Well, I'm going to create three different orbitals because I have three different bonds here. I'll just call them psi1, psi2, and psi3. All right, so how would I construct these? Well, I'm going to build this from a combination of the 2s, the 2px, and the 2py orbitals. Why would I pick those orbitals? Well, 2s is going to be fundamental. It's the lowest energy atomic orbital, so it's going to be the first thing included in any of these artificial atomic orbitals. 2px and 2pz should be. These are included because the molecule is written in the XZ plane. And these represent 2px is something that's oriented along the x direction, and 2pz is something oriented along the z direction. So these, some sort of linear combination of these, is going to enable me to create hybrid orbitals that stick in these directions if I find the right proportions in which to combine these. All right, so what do these look like? Okay, I can define them any way I want. I'm going to define the first one to be up here, the one that's pointing straight up. So it will have a component that includes 2s, and it will also have a component that includes 2pz, but it will not have a 2px component. There's no directionality in this direction for that top bond. All right, what components might work? Well, as it turns out, if I play around with the geometry and I normalize this function, it turns out a combination of 1/3 the 2s and 2/3 the 2pz, both under square roots, will give me the appropriate orbital. All right, now for 2p2, the combination that I might want to render would involve a positive px, so let's make this one be 2 psi2. I'll have again a 2s orbital. I will now have a 2px orbital, and I'll have a 2pz orbital. Now I'll note that since all of these are centered on boron, I'm going to make boron be my center of the coordinate system. So if I did that, then my x-axis is actually up here, and so these f orbitals, these f atoms are actually below the x-axis, so they are at negative z values. So in that case, I'm going to have a negative component here for z. Now, when I work out the geometry and work this out right, and you can do this basically for any geometry, it turns out that the appropriate combination of these terms is square root of 1 over 3 times 2s, square root of 1 over 2 of 2px, and negative square root of 1 over 6 2pz. All right, finally for the third one, I'm talking about this bond over here. So this is my psi 3. And as you might guess, the 2s coefficient is going to be the same. The 2px now I'm on the opposite side of the z-axis. So simply minus 1 over the square root of 2px is the right coefficient, and minus the square root of 1 over 6 of the 2pz. Now, how can I check that these things are oriented in the right direction? Well, one way I might do that is to redraw my xz plane, and note that my 2s orbital is isotropic. That is to say, it doesn't prefer any direction. So all of the directionality is coming from 2px and 2pz. This one has only component in 2pz, so it will be a vector pointed up. And I could define the endpoint of that vector as 0 for 2px and square root of 2/3 for 2pz. All right, that would be one way to denote that. Okay, for these others, I'm going to have a plus square root of 1 over square root of 2 for x and minus 1 over square root of 6 for z, so it would be a vector pointing in this direction. So this is 1 over the square root of 2 minus 1 over the square root of 6. And for the third one, it would be a vector pointed in this direction, 1 over the square root of 2, negative 1 over the square root of 2, and minus 1 over the square root of 6. So you can see that this is producing 3 vectors, and you can check this. I won't do it here, but you can find that, in fact, these are all separated by 120 degrees, precisely the way that we surmise it should be for BF3. So what we've done is we basically now created 3 new atomic orbitals, hybrid orbitals, that are pointed in these preferential directions. Now, one thing that you may notice from this is if I take the squares of the coefficients, say for the 2s, and add them together, that'd be 1/3 plus 1/3 plus 1/3. So in other words, square root of 1 over 3 squared plus square root of 1 over 3 squared plus square root of 1 over 3 squared all adds up to 1. All right, it's telling me that I had one 2s orbital to begin with before I started combining it with these other orbitals. I still have, in effect, one total 2s orbital there. I could similarly add up these 3 components for 2pz, squaring the coefficients. I would have 2/3 plus 1/6 plus 1/6. That also equals 1. Similarly, for 2px, I'd have 1 over the 1/2 plus 1/2, that is the squares of each of these coefficients, and I would again get 1. I always have to have that because I start with one 2s orbital, one 2px orbital, and one 2pz orbital. I'm now fractionating them among new hybrid orbitals, and so the sum of their contribution still has to add up to 1 because I can't just create new orbitals out of nothing. All right. You can show that these functions, in fact, do satisfy the property of orthonormality. They are orthonormal functions, and so that makes them particularly convenient to use as a basis set. But now, in order to, to sort of close this, I want to talk a little bit about the energetics of this. All right, so for example, we're combining 2s with 2 of the 2p orbitals. So here's the 2s orbital, and here are the 3 2p orbitals for a given second row element. Now, essentially what I'm doing is I'm mixing this 2s with 2 of these to create a hybrid orbital, 3 hybrid orbitals that are intermediate in energy. They're intermediate because they contain some 2s character and some 2p character. There is a third 2p orbital that I don't change at all, so it is going to stay up here. All right, and that would be the 2py orbital. All right, these 3 orbitals that I've put in here, we actually have a name for them. We call them sp2, and they're called that because I am mixing one s orbital with 2 of the 2p orbitals, so 1s and 2 p's, sp2. The first one that we talked about would have been an sp orbital for the linear molecule. All right, so when I mix these together, in essence, what I'm creating is a new set of theoretical orbitals. All right, the molecules aren't actually doing this. This is all an artificial exercise. But what we're doing is we're creating a pathway by which these atoms can now combine with other atoms to form a molecule of desired shape. All right, so how might this work for BF3? Well, in boron, I have a configuration in the ground state of 2s2. So in other words, I would have just 2 electrons up here. But now when I hybridize these orbitals, I'll end up with 2 electrons up here. And I'm sorry, I have a third one that's up here. So I'll have 3. It's 2s2, 2p1 is the electron configuration for boron. All right, now if I'm mixing it with 3 fluorine atoms, I'm going to simplify the description of fluorine here. Fluorine orbitals are going to be a little bit lower in energy because fluorine has a stronger stronger effective nuclear charge. So the 2p orbitals on fluorine are going to be down here. Now I'm going to just combine these are all full 2p orbitals on the fluorine side. We've got 3 different fluorines, and I have 1 electron in each of the 3 fluorine atom 2p orbitals that are not filled. All right, so when I combine these in a molecular orbital diagram with these 3 sp2 orbitals on boron, I'll now create 3 bonding sigma orbitals, 3 anti-bonding sigma star orbitals, and I think we can see that I've got 6 electrons now to assign. They're going to fill up these 3 bonding orbitals, and I end up creating 1 single bond for each of the boron-fluorine interactions. All right, so this is a way that we can construct, if you will, a simplified molecular orbital diagram using hybrid orbitals here, which are intermediate in energy between the 2 sets of orbitals that they combine.